In this video, I'm going to cover few questions proving few statements by contradiction. So the first one is, if the integer n is odd, then n square is also odd. So this is what we have to prove, and prove by contradiction means, so what we have to prove here is n square is also odd. We'll start with an assumption that n square is even. Okay, if n square is even, we know we can represent n square is equal to 2k, where k belongs to integers, that z or z is the notation for integers, which means n multiplied by n is equal to 2k. But this cannot be true, because if you multiply two odd numbers, then it gives you an odd number. But if you are saying that the n times n is even number, which means n has to be even number. So this means n has to be even number, which is not true, because it was given the integer n is odd number. So we proved this by contradiction, starting with n square is even, and then we represented n square as 2k, and then n times n is equal to 2k, and we know that the product of two even numbers gives you even number. So if you have 2 times 4, that's even number, but 1 times 3, which is 3, is not even number. So which means here n has to be odd number. In this case, n has to be even number if we want n square to be even number, which means this is true. If the integer n is odd, then n square is also odd. So n square odd implies n square is also odd. So it's something which is actually good to keep in your mind. Okay. The next one is, if n square is even, then n is also even. So whatever you have to show that, then that is the part you need to start with a contradicting statement. So n is also even, so we will start with assuming n is odd. Now if n is odd, which means I can represent this n as 2k plus minus 1. So it could be 2k plus 1 or 2k minus 1. So k belongs to z. And now n square is going to be equal to 2k plus minus 1 whole square. We know a plus b whole square is equal to, or plus minus b whole square. This is equal to a square plus minus 2ab plus b square. So which means if I open this, this is going to give me 4k square plus minus 4k plus 1. And I can regroup them. So here I can take 2 common. So this gives me 2k square plus minus 2k and then plus 1. Now this means this, I got this as an even number, so I can represent this again as n square is equal to 2p plus 1. And so I got n square as odd number, whereas n square was given to be even number, which means again by using the proof by contradiction, we showed that if n square is even, then n is also even. Okay, the next one is you have to show that, or it's more like a proof that square root of 2 is irrational. And now again we need to start with, let's say the assumption is a square root of 2 is a rational number. So if square root of 2 is a rational number, it can be represented as p divided by q. P and q belongs to z, and q is not equal to 0. And if we start with that, because we are saying that square root of 2 is a rational number, so we know the definition of rational number means we should be able to represent this as a fraction. And remember, it should not have any common factor here. So now I can take q on with square root of 2 by cross multiplying, and then you get p square is equal to 2q square. So we got p square, which is equal to 2q square, which means p is even number, because we got p square as an even number, and we know if p square is an even number, for example, if p square is 4, then p has to be 2 times 2. So p has to be even number. So we already know that p is even number here. Now after that, we know p square is equal to, we got p square is 2 q square, which means p is even number. So I'm going to use p is equal to 2k, which means p square is equal to 4k square. So we got p square, which is equal to 4k square. So I'm going to substitute this value in this equation. So we got this, and then we got 2k square is equal to q square, which means again q is even number as well. So we got p as even number, q as even number, which means what? It has a common factor. So p over q, because square root of 2 was p divided by q, and this is even, which means 2 is the common factor, and therefore it cannot be a rational number. It has to be irrational number. So again, by using the contradiction, so because common factor in this case was 2, which means it cannot be a rational number, it will be a irrational number here. Okay, so next one is prove that there is no x belongs to R such that 1 over x minus 2 is equal to 1 minus x. So again, the assumption is, let's say that we have a real solution for this one, and that real solution is A, and which means we are saying x is equal to A is a real solution for this equation. So if x is equal to A is a solution or real solution, which we'll find out, this is what we are doing, proving by contradiction. I'm going to substitute 1 minus A. So 1 is equal to, by cross multiplying, A minus 2. So 1 is equal to A minus 2 minus A square plus 2A. I'm going to move this to this side. So A square minus 3A plus 3 is equal to 0. Now you cannot factorize this, and once you will find the using discriminant rule, you can find the solution. So you got here 9 minus 12 divided by 2, which does not belong to R. Okay, or you can also do b square minus 4ac, and if that's less than 0, which means there is no real solution to this one, which means A is a solution, but it's not a real solution for this equation. The next one is prove that if m comma n belongs to integers, just recall integers are your positive and negative whole numbers. So negative 3, negative 2, 0, 1, 2, 3. So z is your positive and negative integers. Now I have to prove that if m and n belongs to z, then this is not equal to 0. Again, we'll start with an assumption that m squared minus 4n minus 7 is equal to 0. So if this is the case, now we will have m square is equal to 4n plus 7, and I'm going to rewrite this as 4n plus 6 plus 1, and then I got m square is equal to 2 common, 2n plus 3 plus 1, which means m square is odd, which implies m is also odd, and I'm going to replace m by 2p plus 1, and I'm going to again substitute this value in the given equation. Maybe here we can substitute here or in the given equation, because we have to show that this is not equal to 0. So I'm going to substitute this here. So we'll get here 2p plus 1 whole square minus 4 into 2p plus 1 minus 7 is equal to 0. When we open this, this is 4p square plus 4p plus 1 minus 8p minus 4 minus 7 is equal to 0. And you will get that as m is 4p plus 1. This is not. So this will be your n. So I'm going to rewrite this. So you still got, yeah, this was okay. So you will get here, so you are going to get here 4p square plus 4p plus 1 minus 4n minus 7 is equal to 0. So this is what you get here. Now from here, I can see what is common here after simplifying this. So we got 4p square plus 4p minus 4n minus 6 is equal to 0. And 2 is common. So I can take this 2 common. I'm going to write this here. So now here you have 2 common. So you get 2p square plus 2p minus 2n minus 3 is equal to 0. Now from here 2 is common. So p square plus p minus n minus 3 is equal to 0. So I got 2p square plus p minus n is equal to 3. Now this is not possible. You cannot have 2 times something is equal to 3, because it's an even number left hand side and right hand side is odd number. So even number cannot be equal to odd number, which means again by contradicting the statement with starting with m squared minus 4n minus 7 is equal to 0, we reach to the conclusion that even number is equal to odd number, which is not true, which means m squared minus 4n minus 7 is not equal to 0. Okay. So the next one is here, show by a counter example. So here we have to show, and we have to give the examples here, so we don't have to prove anything. Show by a counter example the following statements are not true. So if n belongs to z and n squared is divisible by 4, then we need to show n is also divisible by 4. Now if n squared is divisible by 4, then n has to be divisible by 4. Now if I start with n is equal to 6, so n square I will get is 36, and 36 is divisible by 4. 36 is divisible by 4, but 6 is not divisible by 4. But this is not the only example. You can have your other examples also. So we started with a number, any number, because they said n is divisible by 4. So I'm doing because of the contradiction. So I started, let's say n is equal to 6. So there can be other examples also, but n is equal to 6. N squared, which is 36, 4 times 9 is 36. So it is divisible by 4, but 6 is not divisible by 4. Then the next one is if n belongs to z. Again, you can have other example also. Then we have to show n squared plus 1 is a prime number. So let's say that when n is 3, then we get 10. 3 square plus 1, which gives me 10, but 10 is not a prime number. So 10 is not a prime number here. Okay, next one, they asked you if an integer is a multiple of 10 and 12, then it is also a multiple of 120. Now again, if I take an example of 60, it is divisible by 10 and 12, or is a multiple of 10 and 12, but it is not a multiple of 120. So that's it for today's lesson.